That statement was an excerpt from a letter to Pernickel de Bessy from Pierre de Fermat, dated October 18, 1640. Together with that letter was a proposition: P divides A raised to P minus 1 whenever P is prime and A is a co-prime to P. In 1736, Euler first published a proof regarding Fermat's statement. However, a virtually the same proof was given by Leibniz on an unpublished manuscript before 1683. Kurt Hensel in 1913 first introduced the term Fermat's little theorem with the following statements. Before, some mathematicians independently made the related hypothesis. They assumed that if P is prime, if and only if 2 raised to P is congruent to 2 mod P. Hence, the if part of the hypothesis, however, is false. In 1820, F. Sarus proved that 2 raised to 341 is congruent to 2 mod 341, which is true, but 341 is not a prime. He also concluded that 341 is a pseudo-prime. Here, the discovery of pseudo-prime happened. Enough of the historical background of development happened in Fermat's little theorem. So let's move to the proof of the theorem. We want to prove the Fermat's little theorem. The statement is, for any integer a and any prime number p, there exists a raised to p is congruent to a mod p. The proof is, since p is prime, then we are sure that there are only two possible positive divisors of p, which are 1 and p itself. Symbolically, the GCD of a and p is either p or 1. Let's take the case that the GCD of a and p is p. So, if the GCD of a and p is p, then we can say that p divides a. Since p divides a is congruent to 0 mod p. Using the power theorem, a raised to p is congruent to 0 raised to p mod p is congruent to 0 mod p. So, that is an easy proof. So, let's go on to case number 2. Case number 2. If the GCD of a and p is equal to 1, or they are relatively prime, then there exist p minus 1 numbers which are multiples of a. There are a, 2a, 3a, up to p minus 1a. Suppose Ra and Sa are the same modulo 5, then we have R congruent to S mod P. So, the P minus 1 multiples of A are distinct and non-zero. That is, that must be congruent to 1, 2, 3, up to P minus 1 in some order. Symbolically, A times 2A times 3A up to P minus 1A is congruent to 1 times 2 times 3 up to P minus 1 mod P. Rewriting it, we have A raised to P minus 1 times the factorial of P minus 1 is congruent to the factorial of P minus 1 mod P. Using the cancellation theorem, we got A raised to P minus 1 congruent to 1 mod P. Multiply both sides by A, we have A raised to P congruent to A mod P. Therefore, the theorem is proven. There are many ways to prove Fermat's little theorem. The method used in this discussion was using modular arithmetic. So that's all. Thank you for listening. I'm Del Ian M. Aroy.
Are you ready? Are you ready? Are you ready? Are you ready? Are you ready?